Okay, so we have our first example. So a parabolic cable is subjected to a uniform load of 10 kilonewtons per meter. Determine the tension developed at A, B, and C. Okay, so you have here your parabolic cable wherein your points or your pins are of the same elevation. Okay, the span is 20 meters. Okay, and then the difference in elevation between your pin supports and the lowest point is 5 meters. So your task is to determine the tension at A, B, and C. You have here A, you have there B, and then you have there C. Okay? Now, of course, if you try to have your reactions, okay, so you have here your vertical reaction and then your horizontal reaction, your vertical and then your horizontal, okay. So taking summation forces vertical, okay, you would know that these two would be carrying the vertical load and then these two would cancel each other out. Okay, so they are equal in terms of magnitude, but we don't know the magnitude yet. Okay, so starting with, so let's begin by passing a section through A because it's the easiest way to calculate your tension at the lowest point. So if you pass a section here, okay, isolating this one, taking it as one free body, you would have here your system. Okay, so you have your 10 kilonewton per meter. Okay, so again, you have your reaction. Let's denote this one as R. Then you have your tension at the lowest point. That would be T. And then you have here your resultant for the 10 kilonewton load. Okay? So 10 kilonewton per meter load, calculating for its resultant, it would be acting at the center of gravity. Since it is rectangular, and then you have taken half of 20, this one now is 10 meters, correct? That one is 10 meters. Now, for the center of gravity for a rectangle, your center of gravity would just be found or will be found at the mid-height and the mid-span. Okay, so for the span of 10 meters, it would be 5 meters with respect to this particular edge. Okay, so let's denote this one as Q. Okay, so Q now, calculating for Q, Q is equal to your uniform load, that is 10 kilonewton per meter. Multiply that by your width, that would be 10 meters. So you would have Q to be equal to 100 kilonewtons. Okay? Next, we can calculate now for tension T by what? Taking summation moment at your pin support. Okay? So if you take summation moment at your pin support, you would have the elements which would be on the, let's say, on the clockwise direction with respect to or about point B. This is point B practically. About point B, on the counterclockwise you have T, and then on the that would be on the clockwise rather. On the clockwise direction you have T, and then counterclockwise you have Q. Okay? So with that particular equation, you can calculate for T. So taking summation moment at B, basically that one is B. Taking summation moment at B, that would be equal to 0. Let's take positive clockwise. On the clockwise direction, you have the T. Lever arm for T is basically, this is the place wherein you found your T. So with respect to B, your lever arm is 5. Okay? And then next, minus. On the counterclockwise direction, you have here Q. Okay? Try to project that one. You have here Q. Lever arm for Q is from this line of action with respect to point B, that would be 5 meters. That would be equal to 0. Okay? So basically, 5 and 5 cancel. T is equal to Q. Your tension T is equal to 100. So basically, that one is already your answer for letter A. Okay? So that would be the tension developed at A. Next is to calculate for R. Okay? Now, to calculate for R, you can make use of your force polygon like what I discussed a while back. Okay, so you have here Q is downward. That one is 100. Next, going to the left, you have T. That's going to the left, you have there T. That is also 100. So this one is downward, this one is going to the left, then this one is perpendicular. Then you have here your resultant R. Okay, basically common sense will tell you that R can be calculated using Pythagorean theorem. That is the square root of 100 square plus 100 square. Okay, so R is equal to, that is 100 square root of 2. Okay? Okay. Now, if you try to make use of approach for another approach, let's say summation forces and summation, summation forces, you would have your components for R. Again, components for R, you have your horizontal component and your vertical component. Okay, so let's say that your horizontal component is HB and then vertical component is VB. Okay, so since you're expressing or you're analyzing the system with respect to, or by making use of the components, you try to have an analysis without considering R because it is expressed in terms of its components. Okay, so taking again this system as if your free body, summation forces vertical is equal to 0. Let's take positive upwards. On the upward direction, you only have VB. On the downward, you have Q. So you can conclude that VB is equal to Q, wherein VB now is equal to 100 kilonewtons. Okay? Next, taking summation forces horizontal is equal to 0. You have here, let's say positive going to the right. To the right, you have HB. To the left, you have T. So you can conclude that HB is equal to T. Where in this case, you have here T is equal to 100. Then therefore, HB is also equal to 100. Okay? Then calculating for resultant R, again, that would be Pythagorean theorem. VB square plus HB square. You have here VB square plus HB square. So R is equal to what? The square root of 100 square plus 100 square. You would have R is equal to 2, or 100 is square root of 2. Okay? Okay, so we have now calculated A, tension at A, and then tension at point B. Now, how do you calculate tension at point C? Okay, so what we can do is, again, pass a section. Since you have already calculated for the tension at the lowest point, if you pass a section at C, okay, pass a section at C, you can either get this side or this particular segment, or you can get this particular segment. Any segment would do. Okay? Okay, so let's just make use of the two segments. Let's make use of the other segment as our way of checking if our answer is correct. Okay, so let's take first this one. Okay, from A to C. Okay, so basically, you would have a free body diagram which looks something like this one. Okay, so again, okay, so you have that one as your system. You have that one is point A, and then this one is point C. Okay, so at point A, you have calculated for the tension at point A, that is T. Okay, and then at point C, you don't know the tension at point C, that would be tangent again. Let's denote this one as tension at point C. Okay, TC. Okay, again, your reaction or your equivalent resultant or equivalent concentrated load for your uniform load, which is 10 kilonewton per meter, would be acting at the centroid. Yeah. Which is, again, Q. Okay. Q prime. Let's denote that one as Q prime. Okay? So Q prime in this particular case, Q prime is how much? Now, going back to the figure, you have here 5 meters with respect to B. Okay? A is 10 meters with respect to B. Okay? Since that one is the midspan or the midpoint of the span, then you can conclude that this one to this one is also 5 meters. Correct? Okay, so going back, Q prime now is equal to, you have here span, that is 5 meters. You have your uniform load magnitude, that is 10 kilonewton per meter. So basically, you just calculate for the area of your load diagram. That is 10 kilonewton per meter. Multiply that by 5 meters. So meter and meter cancels. Q prime is equal to 50 kilonewtons. Okay? Next, since you have now Q prime, you can make use again of your force triangle. Okay? On the downward direction, you have 50. Okay? Going to the left, you have their T, which is 100. Okay? Then you have tension at C would be this line which closes your force polygon. Okay? So basically that is TC. Therefore, TC is equal to the square root of, you have 100 square plus 50 square. Okay? So you would have value for TC to be equal to, that one is 50 square root of 5. Okay, so 50 square root of 5. That would be the value for TC. Again, if you can make use of, if you want to make use of mechanics, TC can be broken down into its components, vertical component and horizontal component. And then with that, summation force is vertical. You would have vertical, you have the vertical component of TC and Q. So vertical is equal to 50. And then horizontal, you have this one and that one. So basically, horizontal component is equal to T. That supports the argument a while back that every horizontal component is equivalent to T. Okay? So you have here vertical to be Q, horizontal and T as T, and then tension at C would be equal to the square root of, or the making use of Pythagorean theorem. You can calculate for TC. Okay, so let's make use of the other side. Okay, let's see if they are or they have the same answer. Okay, so so if you try to make use of the other section, okay, you would end up having a free body diagram which looks something like this. Okay, so again, we have calculated the values for the reaction. You have here VB and HB. So VB in this case is, how much is VB again? That's 100. HB is 100. So VB, that would be upward. That is VB. And then sideways going to the right, you have HB, which is 100. Now we are calculating for TC. Again, TC is tangent to that particular point. Let's note that one as TC. Okay? Then you have your uniform load. That one is 10 kilonewtons per meter. Sorry for that. You have this one to be 10 kilonewtons per meter. And then you have your segment having a span of 5 meters. So based from the figure, that one is 5 meters. So you have here now, let's denote again your equivalent concentrated load as Q, let's say double prime. Q double prime is equal to 5 times 10. Again, Q has a value of 50 kilonewtons. Okay, so with this, again, you can break down your TC to its components. You would have here horizontal component for TC and then vertical component for TC. Okay, let's denote your horizontal as TCX and then vertical as TCY. Okay, and then you can make use of, these components to calculate for your resultant or your tension at C later on. Okay, so having summation forces horizontal first. Horizontal is equal to 0. Let's take positive going to the right. Okay, to the right you have HB. To the left you have TC. There are only two horizontal forces. You can conclude that TCX is equal to 100. Okay? Again, that supports my statement a while back that every horizontal component at every point would be the same. Okay? Next, taking summation forces vertical is equal to 0. Let's take positive upwards. On the upward direction, you have VB. On the downward, you have TCY minus TCY. And then, you have minus downward is Q double prime is equal to 0. So you have here values for BB, that is 100, Q double prime is 50, transposes to the other side of the equation. TCY is equal to 100 minus 50, which will give you 50 kilonewtons. Okay? So therefore, you can calculate now for TC is equal to the square root of 100 square plus 50 square. So TC is the same, that is 50 square root of 5. Okay? So again, basic observation, your horizontal component is the same, okay, in terms of values all throughout the span or all throughout the stretch of your cable. Okay, and then if you try to notice also, TCY is 50 square root of 50. What is 50 square root of 5? That one is equal to 111.8033. And then R there is 100 square root of 2. That is 100. R here is 141.42. Okay, so comparing the 3 points A, C, and B, A has a tension of T, which is 100. A has a tension of 100. Okay, that is for A. C has a tension of 111. And then B has a tension of 141. So that again proves the statement a while back that the lowest point has the lowest tension and the highest point has the highest tension. Since you have here the lowest point to be 100, highest point is this one, and then midway or in between B and C, or B and A, is C, which has a magnitude which is in between 100 and 141. Okay?